Hi everyone, and welcome to Eric's Electronics Workbench. So I recently picked up this Hewlett Packard 66312A DC power supply. It's actually known as a dynamic measurement DC source. It's basically a linear DC power supply with some built-in measurement capabilities and a very accurate readout display. So I thought it'd be useful to have on the bench. But it was sold as not working. It has some kind of a voltage regulation problem. That's what was mentioned in the listing, and some kind of damage to the front panel binding posts. So let's get started with the repair. So let's take a quick look at the front and back of the power supply. So obviously the display area right here, rotary encoder for making settings and adjustments, main power switch, keypad for data entry, and the binding post right here for the main output. And this binding post looks like the one that was mentioned with the damage to it, and you can see right there it's kind of a flattened off area, so it looks just to be cosmetic because this turns okay and it would be usable, and this one doesn't seem to have anything wrong with it either. So let's not worry about this for now. This is easily replaceable, or maybe I can even make that plastic kind of round back out again. I'll have to take a closer look, but again, it looks like just a cosmetic issue, so we'll start in on the troubleshooting and deal with this later on. And let me just turn this around. On the other side, this is a really heavy power supply. I think it's about 25 pounds, and it's rated up to 2 amps of output, so that's the heaviest 2 amp power supply I've ever seen. Must have a huge transformer inside, and it is a linear design, which is why I was interested in it. Very low noise output. So on the back panel, exhaust area out here for the hot air that comes off of the heatsink for cooling, GPIB, serial port. I think this connector right here, it says inhibit and fault. There's some markings above it right there. Main AC line input, fuse, and it says the line setting is set for 120 volts, and I'm in North America, so that is correct. This can be set to other voltages internally. And main output right here, so I don't have the connector that plugs into right here. That can be obtained, and this is just in parallel with the front panel output, but this gives you remote voltage sensing, which you don't have on the front panel. And this remote voltage sensing can be handy because that can compensate for losses in the leads, going from the power supply to the load. And there's a remote and local voltage sensing switch right there. So it says when it's in the local mode, and when out would be remote. So I want to leave that on the in setting. So this plug that goes in here has some screw terminals on it that you can attach your wires to. So I may need to get one of those, but at least we do have the front panel to make our tests, so we don't have to worry about this right now. All right, so let me get this connected to my electronic load, and let's power it up and see exactly how it's behaving. All right, so I have the power supply connected to the electronic load, so let's check it out and see what the problem is. So something interesting on these binding posts, I noticed that both of them have a red colored ring, but the top binding post is the positive output and the bottom one is the negative output. Usually the negative would have a black colored ring just for visual identification, so I don't know why they chose to have a red colored ring on both of them. There is a polarity symbol marked over on the side right there. Now this power supply can sink current as well as, of course, sourcing current, but sinking current means that the connected voltage is higher than the program voltage, and in that case current will flow back into the power supply. And internally there's a transistor, it's known as a down programming transistor, and it will conduct and basically just dissipate that current away as wasted heat into the heatsink. But when you're sinking current into the power supply, the polarity would still be positive on the top, negative on the bottom. You wouldn't flip the polarity, so I don't know exactly why they chose the red color for both of them. All right, so let's power up the power supply, see what happens here. Okay, so we get a self-test on the display, address. Okay, so no faults, no error codes, so that's a good start. And the display looks normal at this point, so it says DIS for disabled, so the output is off. You can see there is no output voltage, and of course no current. This isn't turned on yet. So this has a negative symbol, and it's a minus, and then just down in the microamps, so basically no current flowing. Now, this probably needs to be calibrated, and I intend to calibrate it once the repairs are complete. So ideally, I suppose this should be sitting at near 0 over here as well. And it is normal in these power supplies, even when they're working perfectly correctly and everything, that these sit with the output disabled with a small millivolt value sitting over here. So again, that looks perfectly normal at this point. So let's go here to voltage, and let's say like 10 volts. That'll be a good starting point. So go number entry, and we can just go 1, 0, and enter. And of course this display is showing the readback from what the output is, so the output's disabled, so you still don't see the value on the display yet. Again, perfectly normal on that. It's still sitting at 0. And the current, let's put the current up to 2 amps. So we'll go here, it's the output current, and we will go number entry 2 and enter. So that should be perfectly fine. So you can always check those values. If you hit voltage, it's at 10. Current is at 2, so everything looks good there. So let's output on off. I don't know if you can hear the fan is running also in the power supply, but the microphone might be blocking out that noise. It has a noise canceling. Okay, so we actually do have an output voltage, so that's good to see, and it matches 10.53, 10.54. So very, very close on those numbers, no problems there, but that's not what the program voltage is. It should be sitting right at 10 volts. These are very, very accurate power supplies. So this is way off. That's not acceptable, definitely a problem. So it should be sitting spot on at 10 volts, and it's really not stable either. It's kind of hunting around. The values are jumping around a little bit. So let's give it some load. Let's say 1 amp. So we'll go over here, current set, go 1 amp. Here, enter, and turn that on. Okay, so it's sitting right at 1 amp, no problems there. This is indicating also about 1 amp. Numbers are almost in agreement there. Again, probably needs to be calibrated, but nonetheless very, very close. The voltage has actually come down. It's settled in closer to that 10 volt value, which is interesting. And a little bit of loss in the cable, so it's normal that this would be down just a little bit. So really no issues there. It looks pretty close. So I turn this back off again. Yeah, the voltage rises up again, so it definitely has a voltage regulation problem. That was mentioned that that was a problem, that the output was, not regulated correctly. So let's try here. Let's go to current set. Let's go all the way to 2 amps. First of all, this needs to go. It's going to basically collapse here if I don't have this over the 2. So if we go to current, what we need to do here is move this over. Okay, that's the maximum current that it'll allow you to set. So now I can go to 2 amps, and this is technically over, and it won't try to current limit. If both of these are in constant current mode, then basically the power supply and everything will just collapse down, and the voltage will drop way down. So go enter, that's fine. So it is turned on. Now it wants to go into constant current mode now. Why is it doing that here? So 2 amps. Let's turn that back off again. It's kind of unexpected, so go here, voltage. Voltage is still at 10. Current was at 2. Well, now it's back to 10, so seems like something's a little bit off there. But anyways, now it's back in the constant voltage mode, a little bit over 10 volts. If we go back over here to turn this on, let's try current set 2 and enter. Okay, now it's allowing that, so those are looking very close, 1.99, this is 1.99, so right at 2 amps. It's holding at 10 volts, so it's able to output the full amount of current, full rated current. There is not a problem, and the voltage settles in, but it's not really stable, it's still hunting around. So yeah, it definitely has a voltage regulation problem. Looks like that's where the issue is at. So let me get the power supply taken apart. I noticed that the rear cover seals hadn't been broken, so that's a good sign. So I'll get the back bezel removed. There's just 2 screws. The top cover will slide off the power supply, and then we'll be able to get inside of it and start some troubleshooting. I'll disable that for a second, and turn that back off again. So on the troubleshooting, my first thought is to check some of the internal voltages. I think that'll be a good starting point. And then the service manual has a flow chart, and it will kind of point you through some different areas, but of course they talk about replacing entire assemblies. That's out of the question. We're going to replace it down to the component level if necessary. So anyways, let's continue on with the troubleshooting and see what we can find out. All right, so I removed the cover from the power supply, and I must say inside it looks very clean. There's almost no lint or dust, so it looks like it was well taken care of over the years. So I did a quick visual inspection, and at first glance, everything seems to be okay. I don't see any capacitors that are leaking or bulged, or any components like resistors and transistors and so forth that look overheated or damaged in any way. All the wiring, connectors, and cables look to be fine. So visually, it seems to pass at the first glance. So then I started measuring some of the internal voltages. I haven't measured all of them yet, but they look to be okay. So they're known as bias voltages. They're basically the voltages that operate the internal circuitry, but the ones that I measured so far seem to be fine. So again, I haven't gotten to all of them yet, but so far no problems with those voltages. Then it occurred to me to take a measurement with the oscilloscope on the output of the power supply. And you can see the scope meter is connected to the front panel binding posts, and the power supply is currently turned on. It's enabled, and it's set to 5 volts. And look at that waveform that's being measured on the output. I don't like that at all. So it's showing 1.54 volts AC at about 87 kilohertz. So that looks like an oscillation is going on in the voltage regulation circuitry. And that would explain why the display is showing the wrong voltage value from what is actually set. So that oscillation is occurring in there. So again, it's set to 5 volts right now. And if I increase the voltage, so if I go here to, let's see, voltage, and then step this over 5 volts, let's go up to say 15 volts. There, enter. So now the waveform has changed and it's measuring a little bit higher frequency. It says it's 100 kilohertz, but still about 1.56 volts AC. So again, I don't like that at all. That definitely looks like a problem. So if I take the output and I turn it off, so disable the output right now, you can see it just completely goes away. So the scope's not picking up some kind of noise or something else that's going on. And then if I enable the output again, it comes right back. Now remember, this is not a switching power supply, so to see 100 kilohertz of some kind of a ripple sort of a voltage that's coming out of the power supply, there's no high frequency switching that should be going on in this power supply. So it's a 60 hertz transformer, a linear type regulator. It should be a very noise-free type of output. So a switch mode type power supply, you might expect to see some high frequency ripple and things going on, but certainly not 1.56 volts. So that's way too high on any power supply. And in this power supply, it should basically be noise-free. So yeah, definitely an issue going on with that voltage regulation circuit. So I'll continue with the troubleshooting. I think I need to take things apart so I can get into the lower circuit board, have a little bit better access to start taking some measurements and see what I can find out, concentrating on those components and circuits that are related to that voltage regulation. So I'll continue on. All right, so I removed the A2 circuit board. That's the board that sits in this corner right here. So here's that board. With that board out of the way, I was able to have a better view into this corner, study some of the circuits and components. What I discovered is that there's 2 resistors that are missing. They're right in this area here. In just a moment, I'll get the camera zoomed in a little bit closer and you can see those locations. They're both through-hole components, and it's not that they weren't populated. They were installed at one point, and then they were cut out of the circuit, so the leads are still there. And there's a component identification number next to each one. And I suspect they were both the same value because I took my ohm meter, did some measurements, and they seem to be related to the voltage regulation circuit on the sensing lines. And there's a positive sense line and a negative sense line, so you can see the same circuit basically duplicated twice that's related to those sensing lines. And the other surrounding components, near each resistor are duplicated twice. So I imagine both of these resistors would have been the same value, but what was that value? I don't know. Now, unfortunately, I don't have a complete schematic for this power supply. The Hewlett Packard manual that's online, it's a service manual. It doesn't have a complete schematic. There's just some block diagrams in it. So I don't know what the value would have been, and why would those have been removed? Are they not needed, or was somebody in this power supply, before and messing around and, removed them for some reason? I really don't know what's going on with that. So let me get you zoomed in a little bit closer, and then you can see the location of those 2 resistors. All right, so here's a closer look at the locations of the missing resistors. So on the circuit board right here, you can see there's a cutoff lead there, and then right here. And there's a marking in the middle where the resistor would have been that says R375. And then right here you can see it says R358. The same deal, there's a cutoff lead there and another lead right there. So are these missing resistors the reason for this oscillation and unstable output voltage, or are they simply removed at the factory and not needed? So I removed the A1 circuit board, and I spent some time taking a closer look at the circuit board. And I also spent some time doing some research online, and I was able to locate the service manual for this model of power supply with a complete schematic of this circuit board. So that's extremely helpful. And I was also able to locate an image on file of this circuit board that someone else removed from a working power supply. And that photo proved to be extremely helpful, and I'll get to that in just a moment. So first of all, correction to what I just mentioned earlier in the video. Right here on this location, I mentioned this was R375 and there appeared to be a component missing right here. Well, that's actually not the location of R375. So R375, you can see it on the board right there, that's actually this resistor right here. And what should be right across here that was cut off of the board is actually R396. So R396 isn't actually labeled on the board. There's no mark for that, but that's what's right here. And I know that because I have a component location diagram, and I'll show you that in just a moment. So what I discovered is that this location right here is not actually a resistor from the factory's original setup. It's just a jumper wire, or a 0 ohm resistor if you want to call it that, but it's just a jumper wire. And same with this location right here, R358, that was just a jumper wire. And then I noticed over here appeared to be another component that was missing, but there's no reference marked on the board, but it's the same thing. You can see a little cutoff wire there and right there. And again, it's the same thing on this component location. That's R331, but again, it's not marked on the board, and it was just a jumper wire. So of course the question is, why are these cut? What was removed out of this? It's taking something out of the circuit. So what's going on with that? And we'll take a closer look at that in just a moment. And then as I was looking over the circuit board, I noticed that right here it says R318, and you can see there's a solder pad right there, or it would be a through hole right there and right there. So there's a missing resistor right here, or was it another jumper? I didn't know. But after doing some research, it turns out it actually is a resistor, but it's missing. Now, when I took a closer look, it really looks like it was never populated. It doesn't look like it was desoldered. If it was, whoever desoldered it did a very nice job. It's very clean. I don't see any flux residue or anything on the board. But that raises a question of why that resistor isn't there. Now, of course, it's possible it wasn't supposed to be populated. I didn't know. So I had to take a closer look at the schematic, and we'll look at that in just a second, and I'll show you what's going on with this resistor right here. And I believe it should be populated. Going to the next thing was that image that I found online. And I don't have rights to that image. I don't want to include it in this video, but if you do a search for this model power supply, you'll probably be able to find it as well. But nonetheless, in that image, what I found interesting is that the board is marked as Hewlett Packard, same as this circuit board, and all of these jumper wires are not cut on that board. They're intact. And this resistor is populated right here. So I really feel that these components need to be restored on here. This resistor should be returned, and these jumper wires should be put back in place. It's certainly not going to hurt anything. It's not going to cause a short circuit and cause the board to go up in smoke or something like that. So I think that should be the next step, is to restore this, the components on here, and then try the power supply and see what happens. Maybe it won't make any difference at all, and there's some other problem going on, but I really feel like the troubleshooting, would just be an endless circle of chasing things without these components installed, at least trying them, and see what happens, if it makes any difference. And it really seems like it could make a difference because of what they do in the circuits, and we'll look at the schematic here in just a moment. So let me show you something on the parts location and a note in the service manual as well. So I'm going to move the circuit board out of the way. So let me get this right here, and what I'm going to do is just touch this down a little bit here. It's all washed out here. Pardon the camera bumping. So I think that's a little bit better right there. I'm going to just zoom this in a little closer for you so you can see. So this is the component location diagram, and it's positioned the same way as you were just looking at that circuit board. So I've highlighted some components on the diagram right here. You can see this resistor. This is that jumper, R375 is right here, and then this is R396, so this has been cut. This is R358, so this has been cut. And then this is R331. This jumper has also been cut, okay? And then this resistor right here, R318, I put a dot on each end, a red dot, and that's missing on the board. And then I've highlighted some other components on here as well. So over here, and I'll explain why in just a moment, but this is R458, C387. This is diode, it's really hard to see from this angle here. I think it's diode D341. The one is really hard to see in this drawing right here, but on the computer I was able to see it. So that's D341. D339, I believe that is right there. 330, 339, I think that's the number right there. And this is diode, what is the number here? 340, I believe is the number right here. It's very hard to see this angle. And then this one is R353. This is a large power resistor right here. Okay, so keeping all of those components in mind, on this next page, right here, see there's a note that's in the service manual. And right here it talks about backdating So on this backdating, it says revision A boards. The schematic sheets in this manual apply to revision B control boards. The revision number of the board is located under the Agilent logo next to the U302, which is an integrated circuit. Revision A boards do not contain the following components that are shown in this manual. Well, first of all, the circuit board I have is made by Hewlett Packard, so that's going to be earlier than Agilent. And I don't see a revision number at all. There's a tag, but I can't make out, heads or tails of what the revision actually is. It's not clear. But notice this component identifications right here that are listed. It says C387, D339, D340, D341, R353, R331, R358, R396, and R458. Those are all the components that you just saw highlighted on that other component location diagram. And some of these, like R331 and R358, those are those jumpers. So what I'm not clear is that in the early versions of the circuit board, were those areas not even on the board? In other words, were there no traces on the board to even have these components? Or are they meaning that the traces go to these locations and the components weren't installed? That's a little bit vague on that. However, some of these components, so for example, these jumpers that are cut, you could say that they're not there. But these diodes, D340, D341, they're on the circuit board. So let me go back over here, and I'm just going to put the circuit board back in place like so. Let me touch this back up again here so you can see this. So I'll get my component location diagram here so I can follow along as well with the locations when I point to them here on the board. So C387 and R458 are right here on the board. So that's these two components right here, okay? So they're obviously populated, they're right there. And the two diodes, D330, I think that is, or 339 and 341, those are right over in here. They're kind of hard to point to. They're right down in here. I think you can see that on the camera. Get this wire out of the way. Okay, so it's these two diodes right there. And then there's another diode, D340, and that's over here. It's right next to this integrated circuit. You're really not going to be able to see it, actually. It's behind this capacitor. It's straight down behind, right over in this area here. So anyway, it's definitely on the board there. It's not missing. R353 is under this capacitor right here. It's this power resistor right under here, obviously installed. I think that covers everything. So the R318 isn't mentioned. So this missing resistor right here, it's not even talked about. It's not on that list of maybe, wasn't there on early versions or anything like that. So, questioning why that's gone. So from that list, move this out of the way again. You don't get to pick and choose on which components are actually installed. Touch this up again here. Sorry for all these adjustments as we're going along here. But again, from this list right here, these components are clearly installed, but some of the jumpers were cut. And it doesn't make sense to me why you would cut some of the jumpers and essentially remove them, but leave some of the other components. This list is, it's all or nothing kind of a thing depending on the revision. So again, I feel that putting the components back the way that they probably should be would be the next step for the troubleshooting, just to see what happens. And then there's one other thing up here just to take a note on, where it talks about the introduction to this main chapter here. It just says, this chapter contains drawings and diagrams for troubleshooting and maintaining the Agilent Model 66312A dynamic measurement DC source and the Agilent Model 6612B system DC power supply. Of course, the model we're working on is this 66312A. It says, unless otherwise specified in the drawings, a drawing or diagram applies to both models and input voltage options. And that's really important, because I was thinking that maybe these components weren't included, or the jumpers were cut and so forth, because maybe it was for one version of the power supply versus another. But on the schematic, that's not the case at all. There is no note saying that they go, for one model or another. So let's take a look at some of the schematics, and I'll show you some more of the details on how these circuits and with these components and what they do. So let's take a quick look at this one right here. I'll bump this out just a little bit here. So you can see this is the voltage monitor circuit, basically the remote voltage sensing circuit. And right here you can see it says R396 and R358, and notice they're actually shown as a jumper. It says 0 for 0 ohms of resistance, but of course those are the jumpers, and these are cut on the board. So if we look, both of these circuits are basically identical, but right here you can see that the jumper comes up and there's a capacitor right here, fairly low value 0.047 microfarad capacitor. And with this being cut and taken out of the circuit, it's essentially removing this capacitor from the circuit. Otherwise, when this is installed, the capacitor is from this point, it's being connected down to this point right here. So of course, putting this jumper in place isn't going to cause some disaster on the circuit board or any damage. But I think it's worth trying, because without it, this capacitor isn't there, it's not doing anything. Now remember, the whole problem is that we have these high frequency oscillations going on, and I'm wondering if this capacitor being put back in the circuit, and along with this one right here, could that have an effect on those oscillations? Be very interesting to see. And there's no note on here mentioning that these jumpers would be installed in one configuration versus another, nothing like that. And this is just a part number right here and right here, okay? Also, something to take note of, if you look at the drawing right here, you can see how the wire comes along, for example, off of this resistor, and then it has this sort of boxed in area that goes all around the wires right here, but then it ends at this capacitor and so forth. And you can see that quite a bit on a lot of these areas here. So those are known as guard traces. You can see the guard trace comes down here to the symbol right there as well. And the guard traces are actually separate traces that go around traces on the circuit board, and there's many of them all over that A1 circuit board. They're very thin traces, and they run very close to the main signal line, or the circuit, whatever the circuit might be doing. It might be the main power output or whatever, but they go around the different traces. The reason guard traces are used is because this power supply is able to measure extremely low currents, and if you have any basically leakage on the circuit board, it can affect those readings. And the guard trace is basically, as the name implies, it guards the main trace from noise and other types of interference and problems. So, this can measure down into the microamps of current, and they want that very, very accurate. So it has all these guard traces in all the critical circuits. Also helps with the stability, the voltage reading, and so forth. These are the voltage sensing lines. So they're used extensively on the board. And then that brings me kind of to the next point. I think before I do any more testing on this power supply, I should clean the board with isopropyl alcohol, because if you have fingerprints, oils, dirt, things like that on the board, it can cause leakage currents, and that can interfere with how the circuit's supposed to operate. Obviously, there's circuits in here that are very, very sensitive. So I'll go ahead and clean the board as well before I do any further testing with it. Now, I don't really think that's the problem, that the board, it doesn't look all that dirty actually, but I've been handling it, of course, and looking at it and things, so I think it'd be a good idea just to clean it. All right, so taking a look at the next schematic right here, you can see this one says output filter. It's mentioned right up here. So the output filter is essentially just a capacitor. Let me get you zoomed in a little bit closer here. This is the main part of the circuit, is just right here in the middle of the diagram. So there's a capacitor right here. It's that very large capacitor on the circuit board that was kind of an oval shaped with the white color. And it's a 50 microfarad. I think it's maybe a mylar type capacitor, something like that. It's not electrolytic. It has a kind of an unusual style, and it has extremely thick and heavy leads that come out of the sides, that attach it to the circuit board. So this capacitor right here is across the positive and the negative outputs of the power supply. So it is acting like a filter, it's a capacitor on the output, but its real purpose is to help measure dynamic changes, load changes, and current consumption that the load might be imposing on the power supply. So, for example, let's say the output that you have connected to a load draws a sudden heavy current, but it's just a very fast spike of current. This capacitor could discharge and supply that current. And when it does so, one side of the capacitor is connected to the positive output, but look at the other side. It comes down here, have this resistor, a jumper, we'll talk about that in a minute, another resistor, so these resistors are in parallel. They join back together, they pass through. This is just a single piece of wire right here passing through this transformer. The wire comes over here and it goes to the negative side and out. So essentially this capacitor is right across the power supply, but if this capacitor has to supply current to the load, that current's going to flow through this wire, and it's going to make a voltage pulse in the secondary. The secondary is probably hundreds and hundreds of turns of wire. This is basically a step-up transformer, like a current transformer. And then this goes off to a circuitry that's monitoring for that those pulses and is able to read, and detect that and make some measurements on those. So if everything's a steady state and there's no change and everything is just constant, you wouldn't have any current flow in or out of the capacitor. It would just be charged up and just sitting there. And then of course nothing's happening here and you're not getting any reading. So that's really the point here. And of course it is acting like a filter as well. Now this jumper is cut. So right here, this is, let's see right here, this is a 1 ohm resistor and this is a 0.1 ohm resistor. So by having this jumper cut, it's taking this 0.1 ohm resistor out of the circuit. It would seem to me like you would want a very low resistance, and putting these two resistors in parallel is certainly going to be a low resistance, but with this out, you have just 1 ohm here. So putting this jumper back, it's going to parallel these two resistors. The resistors are both on the circuit board. Seems like it would be a good idea. You would want that low resistance here. So I'll go ahead and try that as well. Again, I don't think this is having an effect on those oscillations, but it'll be interesting to see how the power supply functions. And these can always be cut again if it seems like something isn't working correctly, but I think it'd be a good idea to try it and put it back. All right, and then the final schematic right here. This is the resistor that's completely missing R318. You see that right here? So this schematic, it says it's the current control schematic. And this resistor, let me just move this down here like so. So you can see there's an op amp right here. Basically, you have a resistor and a capacitor in series, but you can see the output of the op amp comes back. So we have some feedback coming back around here, and this is the negative input of the op amp, positive input right there. So I have a feedback path there, more of these guard traces everywhere as well. So you have this path coming down here as well. You have this resistor, which is completely missing, 1 k ohm resistor. I believe it was marked as 1%, an 1/8 watt on the parts listing. The diode's present, and negative 15 volts, a 14.7 k ohm resistor coming in here. And but with this out of the circuit, this isn't doing anything here. That doesn't seem right, because you have the same circuit here, but the polarities are flipped. So this diode, you can see here, the polarity of the anode and the cathode right here. And then here, it's going the other way. So you have the anode here, cathode on this side. And then here, this one was negative 15 volts coming in. Here we have positive 15 volts, same value resistor, 14.7 K, same as right here, coming in right here. This is a 2.15 K ohm resistor, where this one is marked as 1 K ohm. I'm not sure exactly why the difference on those values, but nonetheless, you can see how these are all in parallel, and then they're all acting as feedback around that op amp. So I can't see that you would take this out. That doesn't make sense. I mean, it's part of how this circuit functions. So I'm going to return that resistor and see what effects that might have. Earlier in the testing, I did notice that the power supply went into a constant current mode unexpectedly. I think you probably noticed that I said something was unexpected when it was operating, and I'm wondering if this had something to do with that, because this does say current control. I'm wondering if this circuit really isn't functioning correctly with this resistor missing. So again, it'd be interesting to return this and see how the power supply functions, and if it is wildly out of spec and doesn't work correctly, I can always remove it. But again, that power supply image that I saw on the photo online of the circuit board, this resistor was installed. All right, so I hope that kind of clarifies where we're at on the troubleshooting, and it's a rather odd situation with these missing components. I've really never come across troubleshooting like this where things have been missing. I have come across things that people have worked on before and made a complete disastrous mess of, but this really, I'm not sure. I'm not sure if this is something that someone was trying to troubleshoot in here and do some repairs on, or really, like Hewlett Packard couldn't have let this go from the factory, with a missing resistor and cut wires. That doesn't make sense either. So I'm not really sure what was going on here, but let's try and put these components back and see what happens. So for R318, that missing resistor, the parts list calls it out as a 1000 ohm or 1 K ohm resistor at 1% tolerance. So 1% of 1000 is 10, meaning that the resistor could vary from 990 ohms to 1010 ohms. So I went through my spare parts bins of resistors, and I couldn't locate a 1 K ohm resistor with a 1% tolerance, but I did find this resistor, which is rated 1 K ohm with a 5% tolerance, because it has a gold band on the resistor. However, if we measure the actual value of this resistor, like so, you can see it's 996 ohms. So it actually falls right within the 1% tolerance range that we'd want to see. So this resistor should be perfectly fine to do the initial testing, so I'll get this installed. And I can always go back later and replace this resistor with a 1% tolerance resistor The power supply is easy enough to take apart, so it wouldn't be a big deal to change this out, but this should be perfectly fine to do the initial testing. All right, I installed the 1K ohm resistor right there, and then the 3 jumper wires that were cut have been replaced, so one wire right there, another right there, and the third wire right there. I also washed down the circuit board on both sides with isopropyl alcohol, so that will remove any contamination like fingerprints, oils, the flex residue, anything that would cause excessive leakage currents on the circuit board. And with the sensitive circuits that are on this board, you certainly don't want any kind of leakage currents that would cause undesirable effects. So let me get you zoomed back out here, and I'll just show you the product that I use for cleaning. So in no way are they a sponsor of the video. It's just a product that I find works very well. It's plastic safe, and again, works very well to clean the circuit board of any contamination. So with the changes that I've made on the circuit board, let's see if it affects how the power supply functions. So I'll get everything reassembled, and we'll continue on with the troubleshooting. All right, the circuit boards are installed, so let's try and power this thing up and see what happens. So let me get my power cord and get this plugged in here. Like so. All right, so the power switch is turned off, and I'll turn on the AC outlets on the bench. Right there. So if you're following along and you're working on a power supply like this, you're definitely doing so at your own risk. Take care and be safe, and just know the safety precautions when we're working on AC line operated devices. So I don't have this connected to an isolation transformer. It's just directly powered right off the AC line. And the reason that I don't want it floating on the end of an isolation transformer is just in case that being isolated ends up causing excessive noise on the output terminals. I'm not sure if that's the case or not, but I just don't want to chance it or risk it and have that interfere with any measurements that we make with the oscilloscope on these terminals. So depending on how the troubleshooting goes and how the power supply functions or what happens, if we get to that point of taking these measurements, I just want this to be earth grounded, because it's intended to have the chassis at earth ground potential, as well as the neutral should be at earth ground potential and not just floating. All right, so let's get this powered up here and see what happens. So turn that there, I think you can see that. All right, here we go. So display self-test, the address, and then normal display. Perfect, good so far. So again, it's normal to see some small value that's shown on there, and then it says DIS for disabled. Also, something that I noticed is that on the camera, the flickering that you see on the display is exaggerated. It's not quite that way when I look at this. This display digit over here is flashing just slowly, but on the camera, it makes it look like it flickers a lot faster. All right, so let's set the voltage here. So let's go to, say, 10 volts. We were using that value before. So hit number 1, 0, and enter. Okay. And then the current, we'll just go to the maximum current setting. So if I just move the digit over, like so, and just turn the rotary knob, it goes to the maximum value, enter. Okay, and let's activate the output. Hey, how about that? That looks really good. So it says constant voltage mode, that's normal. And look at the output, it says 10 volts and then just 3 millivolts, so 10.003. And the current is sitting at a very low value. It's a negative value. Now, I'm sure this needs to be calibrated. Ideally, this should be sitting at 0 over here. But this looks really promising. So it's not hunting around. The value is very, very stable. So off to a good start. So this is a read back on the actual output that it's measuring, and it's sitting very close to the program value of 10 volts. So let's take a reading on the output terminals and see what the actual value is. I'll grab my digital multimeter. And let's see what we have here. You can see that in the display, in the camera. Okay, so let's take a look here. Hey, that doesn't look too bad. So 9.995, very close to that 10 volt value. So again, I think with some calibration, it would bring these values right into where they should be. So that's looking very good. So let's go here, let's take a look at the noise. So if we go here to output like so. Yeah, look at that. I mean, that noise is extremely low now. So that's in the microvolt range, about 200 microvolts it looks like. Perfect, looks really good. Very happy with that. So I think this power supply is well on its way to working again. So we'll go through all the calibration as well, and it looks like that'll probably be the next step. So let me grab the oscilloscope real quick here and just take a measurement on the output as well with the scope. I'll just move this down here, like so. All right, so let's take a look here. I got to turn this a little bit further there so I can see it. Clip in there and see if I can get this to make connection inside there. Doesn't quite want to stay. There we go. Well, that looks really good. So if we go here, we're on AC coupling. Yes, we are. Yep. I have to reach around the camera a little bit here. So yeah, we're on AC coupling, and the input here, it's on 20 millivolts per division. So there is absolutely no noise on the output. Very, very low. That looks outstanding. So compare that to that, 100 kilohertz and all the crazy noise and spikes that we were seeing earlier, and all the oscillations that were going on. Looks like it's all taken care of. So I'm very happy with this. This looks outstanding. So if I speed the sweep time up just a little bit here, just to double check. To a higher frequency, yeah. So no problems. Looks really good. Let me grab my electronic load. Let's put a quick load on here and see if it handles, full output. And if that looks good, then we'll move on to the calibration. All right, let's give the power supply some load and see how it handles it. So enable the output. So it's still set to 10 volts. Go over here, let's go to current set and 1 amp. Enter, turn this on. So it looks very good, no problems there. So it's holding very stable in the output voltage, still sitting at 10 volts. And the current 0.996, 0.994, so nearly in agreement there. So that looks good, no problems with that. Let's go to current set, 2 amps. So right at 2 amps over here, and it pretty much matches over here as well. So that's looking excellent. The voltage is also remaining very stable. Really looks like it is functioning the way that it's supposed to at this point. So let's go to the full rated output voltage to make sure it can do that. So we'll go enter number 20. So perfect. So spot on 20 volts, sitting at 2 amps. So that's the full rated output of the power supply. It's able to achieve that. So looking very, very good at this point. Very happy with the results. So the next thing to do is to calibrate the power supply. So we'll get into all of that next. So this power supply has some measurement capabilities above and beyond what most power supplies have, where you just have the voltage and current readouts. So I was just curious to see how those function. So check this out. If you go over here on the electronic load, you can pulse the output. So what I've done is I set up a pulse here. If we go to shift and set the transient level. So level A, current is no current, so 0, okay? And it remains at 0 for 500 milliseconds. And then the level B is 1.5 amps, so a large step in current, but for just 50 milliseconds, so very, very quick. 50 milliseconds is just a brief pulse. And then it's to be continuous, so it just goes over and over again. All right, so if I go over here, shift, set the transient on, and turn that on. So now that's what it's doing right now, okay? That over and over, those two levels from 0 to 1.5 amps, and then that 1.5 amp pulse is happening very, very quickly. Well, if we take a look over here on the power supply, it's 20 volts. You can see the display over here kind of flickers when that 1.5 amps occurs, but it's not a very meaningful display, you know, and it's not indicating the full 1.5 amps. Like there it was 1.3, there it was just 0.3. It's kind of wherever it happens to catch the reading. And that's what a lot of power supplies would end up doing. The current, you know, would fluctuate like that, but you really wouldn't see what that true, you know, pulse value would be. However, if we go over here, the meter mode is just what it's in right now, so you don't have to press that, but that's just the standard mode. These up and down arrows will scroll through some extra functions and measurement readings. So if I go here to the maximum right there, so amps maximum, look at that, there it is. So it happens quickly, but there's the 1.5, and that's what it displays most of the time. Sometimes it says 1.4, but most of the time it's right at 1.5. And that's exactly what the pulse is. So pretty cool. It can capture very, very fast transients and display them. So before I start on the calibration, I wanted to see what could be done about that damaged front panel binding post. So I've already removed it, and you can see right here on the one side, it's kind of flattened out. It's no longer round. And I thought maybe I could squeeze it and kind of get it back into shape, but no, unfortunately not, because there's a crack in several places in the plastic. So really not much can be done with this binding post. Now luckily there's no damage on the front panel where the binding post fits right here. The plastic is in good condition, there's no cracks or any damage, and same with the circuit board where it attaches on the back. No damage back there either, so just the binding post has a problem. So I went through my spare parts bins and I found these two right here, which are used takeouts, something I disassembled many years ago. It even has some extra hardware that's not needed for this installation. But you can see one has a black colored ring and the other has a red colored ring. And I think I'll use the one with the black colored ring because I already mentioned earlier in the video they used a red colored ring for both the positive and the negative. And you can see on the front panel right here, the polarity marks on the side, you know, they don't really stand out that much, but I like having the visual identification with the black as the negative and then the red with the positive. And if I ever determine that for some reason I do want it to be the red color on both of them, you know, I do have that other one that has the red colored ring, it could be changed. Now, if you're just replacing these binding posts, you wouldn't have to take the front panel apart to this extent, but I wanted to clean things while it was all apart. So the binding post just attaches with a nut to that circuit board right there. So, you know, that's really straightforward just to get to that part. But I took everything apart so that I could clean the display glass. And on the contacts right here on the circuit board, I've already cleaned these with a contact cleaner. They have that gold plating on them, but it had a little bit of a kind of a lint and dusty scum that gets inside there. Some lint around the shaft on the encoder right here. They use a kind of a viscous grease, but it you know, it attracts lint and dust over the years. So all of that's been cleaned up and ready to reassemble. Also the window right here, cleaned this up as well. Had some lint and dust behind it, but that's all clean and turned out very nicely. So if you're not familiar with how you take one of these front panels apart, just need to loosen these metal brackets that are on the side. And then you can move the whole front panel forward. And then there's a ground wire right here. You need to remove that. And this ribbon cable that attaches, you know, to the other circuit board, you need to remove that, and so it can slide out as well. And on some of these, I've noticed on these power supplies that there's a nut on this encoder shaft right here, but this did not have a nut on that shaft. So if there is a mounting nut on that shaft, you need to remove the display window so that you can get to that nut right here. And in this case, of course, it didn't, but on the display window, which I was removing anyways just to clean it, if you look at the back side, there are 3 clips right here, these tabs that stick out there, and this one right here. So you just press those in, and then the display window pops out from the front side. So with the display window out, if you need to get to a mounting nut here, you can do so. I don't think this one was missing. It didn't really seem to need it for the circuit board to stay in place. So the circuit board itself fits into some clips that are in here and kind of put the board in place, and then it slides over. But it seemed to fit, you know, very snugly and, you know, was not prone to moving. But I'll double check, because if it looks like that nut should be installed, I'll go ahead and take care of that as well. And on the keypad right here, you never want to clean these carbon contacts, those little black round dots that are on there. You don't want to mess with those, but it's perfectly fine, again, to clean the contacts that are on this circuit board over here. If these keypads ever get intermittent or you have to press the button numerous times, usually it's just because the contacts are dirty on the board, but sometimes the keypad itself can actually wear out. And if you have to change the keypad, it just fits in here. You can see how that corner lifts up right there. So they're very easy to change as well. All right, so I'll get everything reassembled, and then we'll continue on with the calibration. All right, let's go through the calibration process. So the power supply and the Keysight 34465A digital multimeter have been turned on and warming up for over a half an hour. That gives everything a chance to stabilize. And the Keysight digital multimeter is under a factory calibration, so it's definitely known to be accurate. Now, when you're doing this calibration, there's only one external component you need to use, and that's a resistor. There's a chart in the manual that explains which resistor value to use depending on which power supply model you're working on. So for this particular model, you're supposed to use a 1.1 k ohm resistor. I have that resistor right here. You can see it's just a typical precision half-watt resistor. And I think you could also use a quarter-watt resistor. I grab the test leads right here. The reason that the numbers are jumping around is because the leads are floating, and if I join them together, you can see the value falls to a very low, basically zero value right there. But anyway, go to ohms function. So if I take a reading on this resistor right here, so you can see 1.1 k ohms, no problems there, very accurate. So if this resistor isn't accurate, then the calibration would of course suffer, and you definitely need that resistor to be as close to the value that's given as possible. Now, something to make note of is that I'm going to do the calibration using the front panel binding posts, but the calibration is supposed to be done on the rear panel output. Now, the rear panel output needs a connector, and I don't have that connector. It's on order, but it'll be here, probably another week or so. And I don't want to wait that long to complete the video. So again, I'm going to do the calibration on the front panel binding post, and I think it'll be quite accurate, but once that connector is here, I'm going to redo the calibration just to make sure that it's 100% as accurate as possible. And the reason I think that they don't want you to do the calibration on the front panel output is because there's about a foot of wire that goes from these terminals to the circuit board, and that can't be compensated for. There could be some losses in that wiring. And on the rear panel output, you have the remote voltage sensing, and the accuracy is spot on right at those terminals because of that remote voltage sensing. But nonetheless, I think it'll be perfectly fine to do at least a first run through on the calibration using the front panel output. And the steps for the calibration right here in this manual, I just printed them off. So this is in the user manual, not the service manual. So let me set the test leads back over here. So the first page is just explaining some menus to go through, and then the second page gets started here into the calibration. So it says here, reset the unit by selecting the output, scrolling through reset and pressing enter. So select output, there's reset, press enter, so power supply is in a known state. It says press output on off, turn the output on, there it is. So output is turned on, it's enabled. It says to begin the calibration, press the shift cal, so shift and cal. Scroll to cal on, which we're at. And then it says to press enter, and assuming that the password is correct, and the password is set to 0, and that's the default, so let's find out if it has been changed or not. Enter, and yes, we're in. So it says cal. So if the password is incorrect, it'll say cal denied or out of range. And there's some internal switches that you can move to work around that kind of an issue and reset the password. Luckily, we don't have to deal with any of that. So now it says to connect the digital multimeter in the DC volts mode directly to the DC source. Do not connect the load resistor or current shunt. Also, I'm not going to be using the current shunt. I'm just going to rely on the current measurement of this meter when we get to that point. So let me reach around on the other side of the camera here. I'm going to change these test leads. Let's get this back to DC volts. Get this plugged in right here. The test leads are wrapped around each other as well, just to help eliminate any noise pickup. Okay, so gets everything connected there. It says to press shift cal, so we'll do that, shift and cal. Scroll to cal volt. Right there, press enter. It says press shift cal, scroll to cal level, oh, right there, and it says it should be on cal level P1, which it is. Press enter to select the first calibration point. Press shift cal, so scroll to cal data, there. And it says press enter number. And enter the voltage value displayed on the digital multimeter. So we do have a nice stable reading over there. So we have, we won't enter that leading 0, so it'll just be 1 decimal point 434 1. It says 10. It's sitting at that. 11. Let's say 10. Looks like it moves just slightly on that last digit. Maybe 11. We'll go with that. That's okay. So we'll do enter. It says press Shift Cal. Scroll to Cal level. Use the down arrow to scroll to P2. So it's not this arrow, it's this arrow right here. P2. The second calibration point, and press enter. It says press Shift Cal. Scroll to Cal data. Press enter number. And enter the second voltage value on the digital multimeter. So 17.1256. 1256. Enter. Okay, so that's everything for the voltage programming and calibration part. It says the over voltage protection calibration. It says press Shift Cal. Scroll to Cal voltage protect. Right there. Press enter. And then it says, when you press enter, wait for the DC source to compute the over voltage calibration constant. The display returns to the meter mode when the calculation is complete. All right, so it says wait. All right, easy enough. So that's completed. Going to the next page here. All right, so now we're into the current calibration. It says connect the appropriate current monitor as shown in figure B1A. Connect the digital multimeter across the current shunt. So I'm not going to be using the current shunt. So let me go over here to B1A, double check the setup. So yeah, they're basically, it's just going to put the, this meter is going to be in the current mode right across the terminals. Okay, so that's easy enough. So let me go over here to reconfigure that. So the test leads need to move here. So this is going to be in the DC current mode. And I'm going to go down here to this 3 amp terminal right here. And we are on 3 amps. That'll give the best resolution. Power supply tops out at 2 amps, so we're not going to be exceeding that. So yes, of course, this does put a direct short essentially across the output, but the power supply is current limited. It has a constant current setting to it, and that's what they're checking at this point. So the output voltage, of course, is very, very low during this test, and it's basically just the current flow that's coming out of the power supply. Okay, it says to press Shift Cal. Scroll to Cal current. There. Press enter. It says press Shift Cal. Scroll to Cal level. Press enter, and it should be on P1, and it is. Enter. It says press Shift Cal. Scroll to Cal data. It says wait for the digital multimeter reading to stabilize, then read the digital multimeter. And they talk about computing the reading divided by the shunt resistance, but we don't need to do that because this has essentially a shunt in it and it's taking that reading for us. So you can read this directly as the current right there. So now for here, we're going to do press enter number and enter the value. So we have over there, it's in amps DC. So just start with the decimal point. 1, 4, 3, 4, 2, a little bit of fluctuation on the last digit. Looks like it's probably about, maybe about 4. Go with 4. That should be fine. Okay, so enter. It says press Shift Cal. Scroll to cal level. Down arrow again. Second point. Press enter. So the fan speeds up. I don't know if you can hear that with the microphone, maybe noise canceling that out. Actually, we can see the current is up a little bit higher now, definitely. Press Shift Cal. Scroll to cal data. And it says wait for a stable reading, and press enter number. Enter this value. So we have 1.754. 0 and a 1, and that last digit changes a little. Let's see. Went up just a little bit there. Maybe space that 40. What do we have there? $29, $30. Hunting around, maybe 30. We call that about 30 for right now. For 0. Seems like that value is rising up a little bit higher, but then it comes down a little bit there. It's up as high as maybe 3.5 right there, 3.3. Let's talk about letting it stabilize here. We'll just give it a moment. I'm seeing a 3.5 come up quite a bit there for those last digits. Let's go with 3.5. I think that'll be perfectly fine. Go with 3.5 and hit enter. That should be okay. Okay, now the low range current measurement. So I believe this is the point where we're going to need this other resistor. So it says press Shift Cal. Cal current measure low. Right there. Press enter. It says connect the appropriate calibration load resistor as shown in figure B-1B, and then connect the digital multimeter in current mode in series with the load. Let me get things repositioned just a little bit here with this resistor. I need to use some different test leads to clip the resistor in place, and then we'll continue on. All right, I have the 1.1 k ohm resistor installed, so it goes from the positive output of the power supply. It's clipped onto this red test lead. Red test lead goes over here to the positive input on the digital multimeter's current input, and then the black test lead returns back around to the common and negative on the power supply over here. Okay, so let's continue on with the calibration. It says here to make the connections. Okay, we did that. Press Shift Cal, so Shift Cal, and then scroll to cal level. And it says cal level P1. Yep, we're on that. Press enter. It says press Shift Cal. And scroll to cal data. And then press enter number. And then it says just to wait till it stabilizes and then enter the number on the display. Now, something I'm not sure of here, I think this should be entered as milliamps. Okay, this is displaying milliamps, but over here, I think this is in amps, so we need to put the decimal point and then over for the 17 milliamps that we're seeing there. I believe that's how this is supposed to be done. They're not clear on that, but let's try that here. So we go enter number, we're at 0.17 milliamps, is going to be another 0, 1, 7, 6, 5, 2. How many digits does this allow? No more digits. So 652, and that last digit's a little bit unstable anyways. Okay, so we enter, and yes, it did accept it, so no problems there. And then we need to do the AC current measurement calibration, which only applies to the 66312A model, which is the model we're working on. So it says disconnect all loads from the DC source. So go ahead and do that. Like so. It says press Shift Cal. Scroll to Cal current measurement. AC. There it is. Okay, Cal current measure AC. Press enter. It says wait for the DC source to compute the AC current calibration constant. The display returns to the meter mode when it's complete. Oh, that was quick. Okay. And I believe that is the final step. No, we need to save the calibration constants, of course. Don't want to stop too soon here. What do we need to do? So press the Shift Cal. Cal save. Right there, Cal save. Press enter. And then it says press Shift Cal. Cal off. And enter. And we're out of the calibration mode. The cal indicator is gone. So perfect, that completes the calibration. So let me reach around. I'm going to put the other test probes back on and let's see how the accuracy looks. Take a couple quick measurements. All right, let's take a look at the power supply's accuracy now that it's been calibrated. So start with the voltage right here, and let's go, let's say a low value, try number, enter, we'll just go 1 volt, enter. Output enable. So that looks very good. So 0.999 volts, sitting same over there. So no problems there. Let's try something higher. Let's go to 10 volts. So go voltage, enter 1, 0, enter. So again, numbers are basically in agreement, sitting right at 10 volts. Very close. I wouldn't be surprised if this slight discrepancy being off from 10 volts by just a couple millivolts right there could be because the calibration again was done on the front panel rather than the back panel. So again, I'm going to redo that calibration anyways, but still looks very, very close. And let's just go to the full output. So go voltage, enter number, try 20, enter, so 20 volts. And yeah, sitting right at 20 volts there, no problems with that. Let's look at the current measurement ability. So I don't need to connect it to an electronic load. I can just connect it in the current measuring function on the digital multimeter. Yes, that puts a direct short on the power supply, but it'll go into constant current mode, and then we'll still be able to use the readings and compare the current measurements. So let me reach over here, and I'm just going to go down to this right here, DC current mode. All right, so right now it's current limiting at 100 milliamps, and yes, right at 100 milliamps over there as well. So if we go to the current setting, and let's go up to say 1 amp, let's try that. So enter number 1. So you can see how the voltage drops down. It's in constant current mode, so 0.488 volts, but it's holding right at 1 amp. And yeah, it looks very good over there, no problems with that. Let's go to the full output current. So they say current, enter number 2 amps. And yeah, perfect, no problems there, right at 2 amps. Looks very good. Let's see how the voltage has come up a little bit higher, but still constant current mode. Let's try a really low value of current. So let's say, go to current, and then enter number, let's go to point, let's say 0.005, so 5 milliamps. Yeah, very close. So 5 milliamps there, sitting at 5 milliamps over here. We should be able to measure current even lower than that. If I go to this input, current range, what do I do right here? Low current range, let's try that. So now this is reading in milliamps. So you have milliamps, a decimal point, and then microamps. So 5476, 547, yeah, really close. Really, really close. That looks good. Very happy with those results. So let's try this. Let's go to current and then enter number and go 0.000. That'd be milliamps, and then let's go 1. So that'd be 100 microamps. So I'm not sure what the lower limit is on what this can control. Maybe that's it actually. So that's 873 microamps and 876 microamps. So that might be the lowest that it can control for the current. But that looks fine, no problems with that. The numbers are definitely in agreement. So I'm really happy with the results. I think power supply seems to be working very, very well at this point. So with essentially a short circuit on the power supply's output, it was able to control the constant current mode down to about 800 microamps, as we already saw in the video, and entering values into the power supply to control the current any lower, it just seems to ignore. So 800 microamps seems to be about the limit of the constant current mode. But I was curious about the power supply's ability to measure currents even lower than that. So you can see the test setup that I have. It's set to 6 volts. It's in the constant voltage mode as expected. And then this resistor is in series between the power supply and the digital multimeter. So it goes from the positive output on the power supply through the resistor. The red test lead goes over here to the digital multimeter's input, comes out on the black test lead, and returns back over here to the power supply's negative. And we can see the result. This is measuring, it says here, this is in microamps, so it says milliamps, but the decimal point's right there, so it's 0.010, so that's 10 microamps. Fluctuates ever so slightly, but pretty constant, right about 10 microamps. And over here, this is reading directly in microamps, and you can see it's 11.8 and some change. So essentially about 1.8 microamps difference, and that's really, really close. 1.8 microamps is an extremely small value, so very happy with the results. And it actually makes sense. This is a 500 k ohm resistor, just a junk box resistor. I measured it, it actually measures closer to 505 k ohms. And if you take 505 k ohms and you multiply that by 11.831 microamps, you do get very, very close to 6 volts, just using Ohm's law. So the end result looks good. Very, very happy with the measurement abilities of this power supply. So earlier in this video, I had mentioned that this power supply can both source and sink current. So all power supplies can source current, meaning that current flows from the power supply out to an external load. But under certain situations, this power supply will also sink current, meaning that current flows from an external source back into this power supply, and that current is basically just wasted off as heat inside the power supply and exhausts as hot air out the back vent. So here's an example of that. You can see the power supply is set to 6 volt output, but notice the current value that's being displayed. It's a negative value. So that negative value tells us that the power supply is sinking current. It's about 853, 854 milliamps. So why is it doing that? Well, let me move the camera up here. Just pardon the movement. Go up to this upper shelf right here. So you can see my Keithley power supply. So the Keithley power supply is the current source in this case. And you can see it's set to 6.1 volts, so it's 100 millivolts higher than the Hewlett Packard power supply. And because it's a higher voltage, current will flow from the Keithley power supply back into the Hewlett Packard power supply. And notice that the current value being displayed is also the same. It's about 853 milliamps. So if I take the voltage and decrease it, start to go down, notice the current value is now falling. All the way down, so 6.01 volts, about 100 milliamps. And then when I go to 6 volts, basically the two power supplies are the same, and we have just 20 milliamps of current. And if I go any lower, it's 5.9, but it's going to probably go to 6 volts. See, yeah, the display goes back because that's the applied voltage, and the current has now gone completely to 0. Which makes sense because the Keithley power supply cannot sink current, so no current will flow back into this power supply. And so when they're essentially the same voltage, or this is a lower voltage, then no current flows. So the repairs and testing on the Hewlett Packard 66312A dynamic measurement DC source are now complete. I'm definitely looking forward to having this power supply on the bench. I think it'll be really handy to have around. It has some of the most accurate measurements of any power supply that I own, and some extra features as well. So if you enjoyed this video, please remember to give it a thumbs up, and if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Lots and lots of projects in the queue. You won't want to miss any of those. So until next time, take care. Goodbye for now.